So what is this miraculous device? At its core, a stent is a small, expandable, mesh-like tube. Think of it as a tiny, sophisticated piece of scaffolding designed for your arteries. Its job is elegantly simple: to be placed inside a narrowed or blocked blood vessel, and then expanded, pushing the plaque against the artery walls and locking the vessel open. This action immediately restores blood flow, like clearing a landslide from a critical highway. The stent remains in place permanently, acting as a skeletal support system to ensure the artery does not collapse back on itself. The journey of a stent into the body is a marvel of minimally invasive surgery. It begins with a tiny incision, usually in the wrist or groin. A thin, flexible tube called a catheter is threaded through the vascular system, its path guided by real-time X-ray imaging. Mounted on the tip of this catheter, in a compressed state, is the stent, often over a small balloon. The surgeon, like a celestial navigator charting a course through a complex galaxy of vessels, expertly guides the catheter to the site of the blockage. Once perfectly positioned, the balloon is inflated, expanding the stent and pressing it firmly against the artery wall. The balloon is then deflated and withdrawn, but the stent stays behind, a silent guardian. It is a permanent implant, a testament to human ingenuity now integrated into the very fabric of a person's biology. The choice of material for a stent is a life or death decision. Early attempts with simple plastics or unsuitable metals failed spectacularly. The body's immune system is an exquisite detection engine, programmed to identify and attack anything it deems foreign. The first major breakthrough came with the use of surgical-grade stainless steel, specifically an alloy known as 316L. This wasn't just any steel, it was a carefully crafted recipe of iron, chromium, nickel, and molybdenum. The chromium is the key player, forming an incredibly thin, invisible, and non-reactive layer of chromium oxide on the surface. This passivation layer acts like a diplomatic shield, making the metal invisible to the body's defenses. The 316L stainless steel alloy was a brilliant first step, offering the necessary strength to hold an artery open and the corrosion resistance to survive for decades in the warm, salty, and dynamic environment of the human bloodstream. However, science never stands still. Enter the cobalt-chromium alloy. Cobalt is stronger and more dense than iron, meaning stents could be built with thinner, more delicate struts. Thinner struts meant the stent was more flexible, easier to deliver, and less disruptive to blood flow once in place. But the innovation didn't stop there. The quest for the perfect material led to alloys incorporating platinum, which enhanced radiopacity, making the stent easier for surgeons to see during placement. Some advanced stents now use a unique composite structure, featuring a platinum core wrapped in a cobalt-chromium shell, combining the best properties of both materials. Each new alloy, each subtle change in composition, represents years of research and a deeper understanding of the intricate dance between a man-made material and the living systems of the body. A stent's material must do more than just hide from the immune system. It must perform a demanding physical job with flawless precision. Two properties are paramount: strength and flexibility. The stent must be strong enough to resist the immense pressure exerted by the artery wall, which naturally wants to spring back to its narrowed state. It must withstand the cyclical mechanical stress of a heart beating 60 to 100 times per minute, every minute, for the rest of the patient's life. That's over 40 million cycles per year. The material must resist metal fatigue, the same phenomenon that can cause a paperclip to break after being bent back and forth repeatedly. At the same time, the stent must be incredibly flexible. Before it is expanded, it is crimped onto a balloon catheter to a diameter of just over a millimeter. It must be pliable enough to be threaded through the twisting, turning highways of the vascular system without kinking or damaging the delicate lining of the arteries. This is where the geometric design, made possible by laser cutting, works in harmony with the material's properties. Another critical principle is shape memory, a property famously exhibited by an alloy called nitinol, a blend of nickel and titanium. Nitinol stents are self-expanding. They are manufactured in their final expanded shape at a specific temperature. They are then chilled, which allows them to be compressed and loaded into a delivery catheter. When the stent is pushed out of the catheter into the warmth of the body, the material's internal crystalline structure remembers its original shape and automatically springs open with a gentle, consistent outward force. Furthermore, scientists harness the stent as a vehicle for therapy. Bare metal stents, while effective, sometimes cause the body to overheal, creating so much scar tissue that the artery would re-narrow. The solution was the drug-eluting stent, or DS. Materials scientists developed special biocompatible polymers that could be used to coat the metal stent. These polymers act like microscopic sponges, infused with a drug that slowly seeps out over weeks or months. This drug inhibits the formation of scar tissue, dramatically reducing the rate of restenosis. The stent was no longer just a scaffold, it was an active drug delivery platform, a fusion of mechanical engineering and pharmacology. The story of the stent is not just one of clever metallurgy and polymer chemistry, it is a story of human lives. Before the widespread adoption of angioplasty and stenting, a major heart attack often meant one of two things: high-risk open-heart bypass surgery or a future of managed decline with medication, living with a permanently damaged heart and the constant fear of another event. The recovery from bypass surgery was arduous, involving weeks in the hospital and months of rehabilitation. The stent changed that narrative completely. It transformed a life-threatening emergency into a manageable condition, treated with a procedure that could be completed in under an hour. Consider the ripple effect of this innovation. Millions of people who would have otherwise died or become severely disabled are alive, active, and productive today. Parents have watched their children grow up. Grandparents have met their grandchildren. People have returned to their careers, their hobbies, and their lives with renewed vigor. The economic impact is staggering, saving healthcare systems billions by reducing the need for expensive surgeries and long-term care. The psychological impact is immeasurable. The stent provides not just open arteries, but peace of mind, replacing fear and uncertainty with hope and a tangible sense of security. This technology has democratized advanced cardiac care. The procedure is now so routine and refined that it is performed in community hospitals around the world, not just in elite urban medical centers. A farmer in a rural community, a teacher in a bustling city, or an office worker in a quiet suburb can all have access to the same life-saving technology. The stent has become one of the most successful and widely used medical devices in history, with millions implanted each year. It is a silent, invisible part of our global population, a tiny piece of metal and polymer quietly sustaining a billion heartbeats. The stent is a powerful reminder that breakthroughs in medicine are often, at their core, breakthroughs in our understanding and manipulation of matter. The future of stents lies in materials science. Engineers are developing devices that not only restore blood flow, but also dissolve safely, leaving arteries healed and natural. Bioresorbable scaffolds made from advanced polymers hold arteries open and then gradually disappear, reducing long-term risks and enabling natural healing. This revolution in medical materials is shaping the future of medicine, enabling smarter implants, targeted therapies, and a new era of healing.